Hello. Okay, everybody. Thank you for coming. My name is Erin Nissen, and I just finished my PhD at the University of Illinois under the direction of Dana DeLotte. And I was investigating the reactive nature of nitromethane, which is an explosive liquid under tabletop shock compression. So let's get started with the introduction and overview of the tabletop shock compression microscope. So to begin, why should we be interested in nitromethane? So nitromethane is a transparent liquid that when you hit it really hard, it will actually explode. And if you hit it hard enough, it will actually detonate. And people have been interested in nitromethane for decades because it's one of the simplest homogeneous liquid explosives. And because of that, we can use it in order to inform simulation and theory on some of these much more complex explosive materials. Now, because people have been interested in nitromethane for decades, a lot is known about its detonation properties. But what isn't known that much about is its chemical kinetics, so what's going on with the chemistry behind that detonation front. So that's what I was interested in looking at. So if we take a quick look at what we think we know about the chemical kinetics of liquid nitromethane, we can see that two different groups used molecular dynamic simulations in order to figure out that there was a two-stage explosion. Now, there is this first explosion, which is the intermolecular proton transfer between three nitromethane molecules, which results in these intermediate products. And then the OH will cleave from the nitrogen, forming water, and this marks the beginning of the exothermic chemistry. Then there needs to be a second explosion, which breaks up this 40 to 70% of carbon and nitrogen atoms tied up in large molecular fragments. And that results in these stable products shown here on the right-hand side. Now, as a chemist, we would typically turn to molecular spectroscopy, but because of the extreme temperatures and pressures and how fast these velocities are flowing during these explosions and during these detonations, that's just not really a tool that is quite developed yet. It's on its way, but it's not quite developed yet. So what I propose is we use this alternative approach. And without getting into the nitty-gritty details of the alternative approach, I just want to go over the overall method first. So in this approach, we're going to use a flyer plate or this thin aluminum disc, and we're going to impact a cuvette filled with nitromethane. And what will happen is this impact will partially ignite some of the reactions in nitromethane, creating this luminous shock front that will continue to travel through nitromethane. Then a few nanoseconds later, there will be these two delayed explosions, these two-stage explosion. And these two delayed explosions will actually send these spherically propagating shock waves forward towards the original shock front and eventually collide with the original shock front. When they collide, they're going to increase the temperature, luminosity, and density at the collision points. And they will create these structures or these patterns. And these are usually referred to as cellular structures because they have this cell-like shape. And these have been seen before in gaseous detonations, as we can see on the right-hand side, where they actually etch these cells onto the confinement chamber. And we can see why they're called cellular structures because they have this cell-like shape. Now, it has been proposed that these cellular structures exist in pure liquid nitromethane before, but until the work that I published and the work I'm going to show you today, it had never actually been experimentally verified. Now, that's amazing that we were actually able to see these cellular structures. But what's even more important is we can actually use the arrival and the size of the structures to determine when and where the explosions took place behind the detonation front. So now that we know a little bit about why we should be even just interested in nitromethane or the chemical kinetics, how do I actually create these explosions in nitromethane? So my group uses shock waves, and what a shock wave looks like is shown here on the left-hand side, where when the shock enters the material, there's going to be an instantaneous increase in the pressure in the material. And the shock will move through the material at shock velocity u sub s, which is constant for the shock duration, in my case 4 nanoseconds, followed by a relief wave. And that relief wave will bring the pressure back down to 0. Now, the shock velocity for nitromethane has a linear relationship to the particle velocity u sub p, where the particle velocity is just how fast those particles are moving behind the shock front. And A and B are constants specific to nitromethane. Now we can relate the particle velocity u sub p and the shock velocity u sub s to the pressure using this equation on the right-hand side called the Hugonio. Now we can see what a Hugonio looks like in the pressure particle velocity space, where a Hugonio is just made up of lots of different end states from the result of doing different experiments at different input conditions. And the Rayleigh line is actually what describes the compression path from some sort of initial state to some sort of final state along the Hugonio. Now, in order to acclimate you into what types of pressures and velocities we're talking about today, I'm going to first show you this cutout of the Earth shown here on the left-hand side, where what I'm going to be talking about is about 130 GPa, and that's about in between the upper mantle to lower mantle of Earth. And if you're not familiar with geology, you might be familiar with Mach 1, which is about 767 miles per hour or 0.33 kilometers per second. And so today I'm going to be talking about 1 to 6 kilometers per second, which is about 2,000 to 13,500 miles per hour. So how we use these shock waves is using, like I said, the tabletop shock compression microscope, and a schematic of that is shown here on this slide, where we have a 1064 nanometer neodymium DAG laser that's sent through a homogenizing optic. And this actually makes our beam profile have a flat top beam. And we take our flat top beam and we focus it onto our inverted microscope, which houses our sample array. And then from the back side, we can do different diagnostics, such as photon Doppler velocimetry, or PDV, which is basically just a fancier version of a Michelson interferometer. And this is collecting that particle velocity that I was just talking about. We can also collect any of the emission or the light given off of the sample and send that to a high-speed gated camera or an optical pyrometer. Now, when I first got to UIUC, the lab was focused on solid samples, and so I had the task of implementing liquid samples. So let's take a look at what that sample array actually looks like when we study liquids. So what we do is we glue a piece of 25 micron aluminum foil to a piece of glass, and we take that flat top laser pulse and we focus it right at that interface of the glass glue aluminum. And the energy is absorbed and will actually project out this flat aluminum disc called a flyer plate, which is 500 microns in diameter. And this flyer plate is going to fly over the 500 microns of space, increasing in velocity until finally reaching a constant velocity and impacting the sample of interest, which is nitromethane in this case. Now, because I use liquids, I have to have a 9 micron aluminum lid on top of my liquids in order to prevent evaporation and decrease large contact angles. Now, my wells or my cuvettes that hold the nitromethane are 2 millimeters in diameter, and their thickness is dependent upon the capped-on walls. And that can be anywhere between 30 to 500 microns thick. Then from the backside, like I said, we can collect the thermal emission and do PDV, where the PDV can either focus on this interface between the lid and the liquid, telling us what the input energy is, or we can actually deposit 30 nanometers of gold onto the glass and probe how the shock is changing after it transverses through some sort of thickness of nitromethane. And so the key points that I just want to say here about our tabletop shock compression microscope is I can do about 100 shots per day, and the volume is drastically different. I have 6 to 7 orders of magnitude less volume than at some of these larger facilities, and my shock duration is much, much, much shorter. It's 4 nanoseconds versus these hundreds of nanoseconds to microseconds. And I'm not saying that to say one is better than the other. They definitely have their pros and they definitely have their cons. I'm just trying to express the differences between the techniques. So let's get into the detonation properties that I was able to discover with the shock compression microscope with nitromethane. So now I've rotated my schematic, and my flyer plate is now coming in from the left-hand side, and it's going to impact the lid and send a shock wave into the blue, which is the nitromethane. And we can record what that imparted energy is right at this lid liquid interface, which I denoted as the dashed line as input, where we're looking down here at this figure of particle velocity versus time. So we can see right when the shock enters the material, there's going to be an instantaneous increase in velocity, which will stay constant for the shock duration of 4 nanoseconds. And then we can also probe how that shock changes after it has traversed through some amount of nitromethane. In this case, 25 microns. Then we can increase, say, to 170 microns. We can obviously do all of these different thicknesses in between to actually probe how the shock is changing in both space and time. So this is the least interesting graph I'm going to show you today. This is actually when we have no reaction. If you can imagine, there's a shock entering the material, and if there's no reaction, that shock is going to slowly dissipate as it travels through increasing amounts of nitromethane. Now, in the next slide, I'm going to show you this exact same figure. So once again, exact same figure. This is particle velocity versus time, no reaction, for an input of 13 gigapascals. But what we can do is we can increase the power of our laser, increase the energy that we're inputting into the system to 14 gigapascals, and that's where we see our threshold. This is our ignition threshold. And we see here that we have a reaction. And we know that because, once again, here in maroon, we're absorbing some of that input energy, but then there's a large increase in energy in the particle velocity in the system. And that's due to the chemical reactions that are happening with nitromethane. However, there's just not enough of these chemical reactions in order to sustain. And so the shock slowly decreases in energy until about 30 nanoseconds and 170 microns. There's really no difference between the two pink profiles of no reaction and reaction. Then if we increase the energy of our laser even further to about 18 gigapascals, what we see is we actually can reach a detonation. And so we see, once again, we have our dashed dotted line of our input energy, and the maroon figure, there's some of the energy is absorbed. Then we have this large increase in energy in the blue curve. This is those chemical reactions. And then this slowly dissipates into a steady detonation. And we know we have a steady detonation because the wave profile is not changing in space and time. Now, if we take a further look at some of these detonation properties, what I'm going to show you on the next slide is this exact same figure, just extended out into space and time. So once again, this is particle velocity as a function of time. We're just going out to 100 nanoseconds and about 500 microns now. Now, this can be a little bit difficult to look at because there's lots of overlapping waveforms and lots of colors. So what I like to do is just pick out the peak particle velocity and plot that as a function of time instead. And that way we can sort of see some of these dynamic effects that are happening. So we see that the shock comes in at 0 nanoseconds. A lot of that energy is absorbed. Then we have this large explosion, these chemical reactions that are adding energy to the system. And then we slowly reach a steady detonation down here at about 15 to 40 nanoseconds. However, I have a much smaller flyer plates and cuvettes than some of these other gas gun experiments. And so my edge waves come in very quickly and quench the reaction in about 45 nanoseconds. From the edge of the flyer plate. Now, if we take a look at what I'm showing you here, this blue arrow, we can talk about this thing called the time to detonation. So the time to detonation is the time that the shock enters the material until you reach a steady detonation. So in this case, I have a time to detonation of about 15 nanoseconds. That's what this blue arrow is pointing at. And we can compare our time to detonations to other experimental results with nitromethane using this thing called a pop plot. And so on this slide is what I'm showing you as a typical pop plot where you're seeing the time to detonation as a function of input pressure. And if we extrapolate what other previous researchers have shown, we see that the time to detonation should be about 1 nanosecond at the input pressure of 18 gigapascals. However, my results show that we're about an order of magnitude larger than that at about 15 nanoseconds. And so this is telling us that we have reached some sort of fundamental limit on how fast the chemistry and the fluid dynamics can respond to this input shock. And in order to verify that, I did this experiment again, but instead I did it with an even shorter shock duration of 2 nanoseconds, which requires an even larger input shock pressure of 21 gigapascals. And once again, they could not go faster than that fundamental limit of about 15 nanoseconds that I was just talking about, really telling us that we cannot go faster than that. as it stands currently. So the next thing I want to show you is the 3 distinct regions of reaction in nitromethane. And I don't have time to talk about the pyrometry, which also shows the 3 distinct regions. So instead, I'm just going to talk about my high-speed images. So here we have the high-speed images, which are using a 5 nanosecond gated camera with a 2-micron resolution. And there's no external illumination. So everything you see is thermal emission from nitromethane. So we have the flyer plate coming in from the left-hand side, and the shock front is flying directly towards the camera. So the first region of reaction is at that input threshold of the ignition at 13 gigapascals, where the reactions are just starting to go off. There's some hot spots, but there's just not enough energy to maintain them. Then if we increase our energy just a little bit more to 16 gigapascals, this is where we start to see something really interesting. So right when the shock enters the material at about 1 nanosecond, we see these hotspots that start to form. And then they do a really good job of coalescing into this nice, hot, luminous disk. And then at about 6 to 11 nanoseconds, we see the diameter has increased. And this is where we finally see those cellular structures start to form in the shock front. However, this is why we call it subdetonation. There's just not enough of those reactions in order to maintain, and it slowly fizzles out and dies away. Then if we increase the pressure in the system even more to that detonation threshold of 18 gigapascals, this is where we once again can see something similar, and we can see what happens when we have the actual detonation. We have these hotspots that form. They do a great job of coalescing into this nice hot luminous disk, which is larger in diameter than the subdetonation. It continues to grow, and we start to see some of these features pop out. And then 15 to 20 nanoseconds is when we actually see the cellular structure show up in the detonation. And then, like I said earlier, there's these edge waves that come in and they start to interact with the luminous shock front. Now, this is really important and really amazing because this is the first time that we were ever actually able to show that these cellular structures exist in pure liquid nitromethane. And not only that, because I can do 100 shots a day, because I have this really high throughput, high reproducible apparatus, I'm able to actually show that, I mean, I have hundreds of these images. So I'm actually able to show that every time you see these cellular structures at 6 to 11 nanoseconds in the subdetonation regime, every time in detonation, you see these larger structures start to appear. And so we can fully map out the how the flow structure is changing in both space and time using all 3 of these techniques, the PDV, the high-speed camera, and the pyrometry, which I was not able to talk about today. And so that allowed us to actually map out the full time to detonation, or the full shock to detonation. And with that, I'll just say thank you. I have wonderful funding sources. I had wonderful people that I worked with. They were amazing. I love them all. And thank you guys so much for listening.